I'd like to help you work through a problem from the textbook from chapter 4 that's a type of problem that you don't encounter much, but it's going to be important that you understand how to solve this type of problem. So let's go ahead and get started. This is going to be problem 483 in the textbook, and here's a little sketch of it. But first, let's look at the problem statement itself. It says, as shown in figure 483, which is shown below, a 247.5 cubic foot tank contains saturated vapor, that's going to be a clue, initially at 30 pounds per square inch. The tank is connected to a large pipeline carrying steam at 180 psi and 450 degrees F. Now, your intuition tells you that's going to be superheated vapor. Steam flows into the tank through a valve, shown here, until 2.9 pounds mass of steam have been added to the tank. The valve is then closed, and the pressure in the tank is 40 psi. Determine the specific volume in the tank at the final state of the control volume and the magnitude and direction of heat transfer between the tank and the surroundings in BTUs. Okay, wow, that is a lot of words, and here's a sketch, okay? And here's that steam that's being added to this rigid vessel tank through a valve, okay? And we're asked to find Qn, so I've sort of jotted down Qn here on a little bit of a preliminary sketch. And also, what else have I done? I'm showing a 1 and a 2. That's kind of like a state 1 in the tank and state 2 in the tank. Oh, in my little picture here, it says, be prepared for a quiz, test, or exam. So I want to give you a heads up. And that is this type of problem. You're going to find this is a special type of problem. I'll bet you it's no more than 5 to 10% representative of all the problems you're going to have in this course. And it's also going to be very unusual. Even out in practice, this is an unusual type of engineering problem to encounter. But as a mechanical engineer, you need to be prepared to attack a problem like this. Now, on the short term, I am seeing that a number of instructors are assigning this sort of category of problem in quizzes, tests, and potentially on your exam. Some will and some will not. So it's a dice roll. It's a dice roll for you to say, oh, do I need to not worry about this? Well, maybe. Or if your instructor is going to have a problem like this on a quiz, test, or exam, and you don't bother to learn the fundamentals of this, ooh, you're going to be in big trouble. So let's continue on and see how you fully solve this problem from start to finish. Okay, let's look for some key words in the problem statement. First, it says a system. It says a tank connected to an infinite supply of steam. Okay, well, that from that little picture, it says there's something flowing into that tank, but there's nothing flowing out, okay? Do you see that? So in other words, that tank is not a closed system. This is not a closed system problem. It's an open system problem. However, since nothing's flowing out and something's flowing in, it's not steady state, steady flow, where most of your chapter 4 problems are. Most of your chapter 4 problems are steady state, steady flow, where the outflows flow rates exactly match the inflow flow rates. This is not that case. So this would be considered open system transient flow. The substance, well, it says clearly it's steam. So this is a phase change substance we're going to be working with. We'll be using property tables. It says 2 pounds mass of steam are added to the tank. In other words, the MN is 2.9 pounds mass, and there's nothing going out. The assignment says determine little v, the specific volume at the final state. Well, your intuition says that's going to be pretty easy. I'm given the volume I need to figure out the final mass. So the final specific volume is just going to be V over M final. And then it says determine the heat transfer. I'm hoping you're catching on to my clues when you're watching my videos. Whenever in thermo class you see the words find the heat transfer, that is your clue that you're probably 99% sure you're going to have to write the first law of thermodynamics for your problem in order to find Qn. So that's a clue. When you see the word heat transfer, I'm going to be writing the first law. All right, well, let's get started solving the problem. Let's start with a sketch. And so I've tried to redraw the textbook sketch on my own. You should do that by hand, doesn't have to be a work of art. Here's my tank, and I'm showing, of course, steam, H2O in the tank. I'm writing down in the tank that P2 is, the final pressure is 40 PSI. Over here on the side, I wrote down P1 is 30 PSI, and the phase is saturated vapor. So I'll make a note to myself. I can look up little V1 is simply V sub G at P1 from my pressure table. Okay, some other stuff I wrote down. Qn equals question mark. That's what we're looking for. I wrote down W out equals 0. This is just a plain old rigid tank. Do you see this tank lifting a weight? No. Is there a shaft coming out of the tank rotating in a known torque? No. So the work out is 0. I'm going to label that on my sketch. Here is my unlimited supply of steam, superheated vapor is my intuition at 180 PSI and 450 F. Here's the little throttling valve that's allowing steam to come in from high pressure to lower pressure. And I'm showing M in, the amount of mass that came in. And also on my sketch, I can immediately write the continuity equation on my sketch. It says that M2, the final mass in this tank, is equal to M1, the initial mass, plus the mass that came in. And so on my sketch, I made a little check mark, Mn, well, that's given, and M1, that's going to be pretty easy. M1 is simply going to be the volume of the tank given divided by the specific volume initially, and we can look that up. So that's going to be pretty easy to find M2. All right. Oh, in my green text box, it says, let me move my picture here. It says this category of transient open system problem. This is not a closed system. It's not steady state, steady flow open system. This is a transient open system. And in other textbooks, it's called uniform state, uniform flow, USUF. And the reason is that what's coming in here to this tank is always at a fixed state, a fixed enthalpy, a fixed pressure and temperature. That's why it's called uniform state. And also uniform flow. When the valve is opened, the mass flow rate is some number and throughout the process. And so that would be uniform flow. I want to chase you back to your textbook with the time you have available and at least browse, if not dissect, section 4.12 called transient analysis. At least browse it. Section 4.12.1, the mass balance, so that's the continuity equation, and 4.12.2, that's the first law, the energy balance and transient analysis, that's the first law, and I've plopped down a screenshot of what that first law looks like. We'll talk more about that here in a second. Please go to your textbook. If you're having a hard time understanding what does transient flow mean, I don't understand transient flow compared to things operating steadily or a closed system problem. I've tried to create another video, and I see that it's about 30 minutes long, 32 minutes, under my thermodynamics fundamentals playlist to try to give you physically an example of transient flow. So I've tried to do that in real life. Here's a general statement of the continuity equation pulled right out of your book, out of your textbook, and it's worth just mentioning for any general uniform state, uniform flow process. It says that, so this is not your homework problem. This is a general statement. It's a piston and cylinder with masses coming in, masses leaving. It says that the final mass equals the initial mass, m1 plus the sum of the masses that came in minus the sum of the masses that come out. And that's just basically common sense 101. So that's a general statement of continuity for any uniform state, uniform flow problem. The first law for any uniform state, uniform flow transient process. So you see I've got a piston and cylinder with masses coming in, masses coming out. That's the most general type. And so I won't repeat it here because we're going to get into our homework problem specifically, but you can get the general idea of what the first law is all about from the textbook. You see, I rearranged the textbook formula, I hate to say that word, the textbook statement of the first law into something that I find easier to remember. Q in minus W out. Wow, that sounds a lot like a closed system, doesn't it? Q in minus W out equals U2 minus U1, capital U2, capital, sounds a lot like a closed system, plus some extra terms, plus the sum of the M dot leaving, H leaving, minus the sum of the M dot in, H in. So that's just a general statement. So now I don't want to torture you with details you don't need to know to solve the problem, but it's worth writing that down in this video. Okay, so now we're back to our problem at hand. Let's plan our work by writing down the first law. Here's a little bit of a reprise of my sketch and also a reprise of the first law for any transient flow, uniform state, uniform flow problem. So let's dissect it. Q in, well, that's question mark. That's what we're trying to find. W out. Hopefully I've convinced you for this problem, we can strike that out. There is no work. Equals capital U2 minus capital U1. Well, that's just M2 little u2 minus M1 little u1. And I've got those checked off. I think you can see that M2 is going to be easy. U2, we're going to be able to figure out what little u2 is. M1, we're going to be able to calculate that. Little u1, we're going to be able to look it up. The sum of the M dot leaving, H leaving, well, there's nothing leaving. Look at the sketch. I strike that out, minus the sum of the M in, H in. Well, there's only going to be one mass in and one enthalpy in, Mi. So in a lot of ways, it's going to be relatively easy once we've planned our work. Okay, so let's go about the solution. Let's look at state one properties first. We've planned our work. We need U1 and we need little v1. So we'll go to our pressure table since we're given initial pressure, go to 30 pounds, and we will write down V1, 13.75 cubic feet per pound, and U1, 1088 BTUs per pound, right out of the just straight lookups. V1 is given, 247.5 cubic feet. We can immediately calculate M1, the initial mass, is the volume divided by the specific volume. It's 18 pounds mass. Wow, nice even number. Ooh, how convenient. The amount of mass that was added to the tank was given 2.9 pounds mass. So quickly we'll write down, this is the continuity equation. M2 is M1 plus Mn. That's a statement of the continuity equation. It's also common sense 101, isn't it? M2 is simply going to be the sum of these two numbers, M1 plus Mn, 20.9 pounds mass. Critical to write that down in your solution. Working down the page. Next thing is, let's determine the inlet enthalpy, Hn. We've got to divert here a little bit, but notice here where you say, well, here's our unlimited supply of steam, and I've labeled that state X, okay? We're going to go right to the superheated vapor tables, 180 psi, 450 F, to write down Hx is 1243.4. We have to, in our minds, though, we have to think about the first law for this little process here, X to I. Flow across a throttling valve, flow across an insulated throttling valve. fully insulated valve. Here's our first law for steady, uniform flow across through this valve. Q dot in, 0, fully insulated, minus W dot out for this process. Not lifting a weight, 0. So 0 equals M dot, the mass flow rate through the valve. We'll divide both sides by that to get rid of that, times the quantity HI minus HX. And so almost by magic, but by the first law, we've got H sub I, what's going into the tank, exactly equals H sub X. So I've written down in my solution, HN equals 1243.4 BTUs per pound. Okay, so we're getting somewhere. We're well on our way. Okay, now let's see. Let's determine V2, little v2, the specific volume at state 2. We've got given volume of the tank. We just found M2, the mass. I remember the definition of specific volume. It's V over M. Wow. So little v2 is 11.84 cubic feet per pound. We're going to get a 50 on our homework right now because we've got half the problem solved. Little v2 is equal to 11.84 cubic feet per pound. That's the final specific volume requested. Now let's move along because we need to figure out what little u2 is, and then we'll be done using the first law. Okay. We've got two independent properties at state 2. P2 was given, 40 psi, and V2 we just found, 11.84 cubic feet per pound. That gives us two independent properties. You remember from chapter 3, if you have two independent properties at any state, all the other properties are fully determined. So now we can figure out what is U2. Okay, and so here's a repeat of what I just had on the previous slide. Here's my two independent properties. I have a pretty good feel that what's going to be left in the tank, the phase, is going to be a superheated vapor. That's sort of, I've got a feel for that. So I'm given P2. So I'm going to go to my superheated vapor table and look, I found 40 psi, great. And now I've got to shop around for a V2 is 11.84. I've got to use my eyes. And here's my pick list of specific volumes at 40 psi superheated vapor phase. And magic, wow, look at this, 11.84 is tabulated. Thank goodness I don't have to do an interpolation. Ooh, this is wonderful. So this is the nature of a very clever textbook problem, right? So I'm looking for U2. All I got to do is write down 1124.2 BTUs per pound, and I'll scan over here to get maybe some extra credit on my homework. T2 is 350 degrees F. All right, so I've got little U2. I need that for the first law from our planning our work. All right, so that's pretty clever, very appreciative of the author that we don't have to interpolate. So little v2, little u2 is 1124.2 since it corresponds to 11.84 cubic feet per pound. All right, so we're going to apply the first law to solve for our heat transfer. Let's see. There we go. So Q in, that's what we're looking for. W out, 0. M2, U2, both are now known. M1, U1, both are known. M leaving, nothing is leaving. So scratch that out. M in, that was given. And H in, we just found it. It is plug and chug in our solution. So you can see I've written down all of those variables, all of those numbers we found. Turn the crank on your calculator to get Qn equals 305.9 BTUs. And so I've written out in the sentence, the heat transfer in to the vessel, because it's a positive number, the heat transfer into the vessel from the surroundings during the process is 305.9 BTUs. Pretty cool. And so you say, well, that was easy. Gosh, all I'm going to do is jot down these formulas from the video, and I'm going to be done with this problem. I want to encourage you to not do that, because you're not, if you try it that way, you're not learning the fundamentals for taking a quiz or test, and you'd really be sunk. I want to give you a little extra. So that's the end of the homework problem. I'd like to give you a little more idea about continuing to plan or prepare for a quiz test or exam that you might be assigned. All right, the homework problem we just solved was 483. You see that could be classified as a tank filling process. You were filling a tank. At the undergraduate level, the only other type of problem that you would encounter for this type of transient uniform state, uniform flow process would be a tank draining example or problem. And I've tried to give you a little sketch of what that might look like. And so here's a similar tank. Of course, it could be the substance could be an ideal gas or a phase change substance. That depends on the problem statement. If it's a rigid tank, of course, the workout's going to be zero. And in this type of example, there'd be a pinhole leak in the side of the tank. That's classic, a pinhole leak. And it's an air or steam or refrigerant is leaking out of the tank. And maybe the amount that leaked out would be given to you. Okay. But do you see how this is see how similar this is to 483? It's just the flip. In other words, this is a tank draining problem. So I want you to think about, how would you solve a problem like that? Well, let's see. You'd start with a sketch. You'd observe that it is an open system. It's not a closed system. It's transient flow. Only mass is leaving. And the final mass, how would you calculate M2 for this one? It would be the initial mass minus the mass that left. So that would be a little difference. Okay, that's consistent with the continuity equation. And then you'd go right back to write down the general first law that you get out of the book, okay? And you'd start striking out terms for this problem, this tank draining process. The tank's got a pinhole leak in it. Let's see. First law, Qn, either it might be given, or who knows what it might be, or you might have to calculate it. It's a rigid vessel, so we'd strike out the workout term. Same familiar approach for internal energy change of the open system, capital U2 minus capital U1. Let's see, there's nothing coming in, so we'll strike out this term and simply have to worry about M leaving, H leaving. And so this would be the setup for the flip of problem that you just solved. So I hope that helps, and I hope that gets you ready. And why am I doing this? It's because when I teach this course, I'm so busy teaching closed systems, steady state, steady flow, open systems, that we spend very little time on this type of system. So I do not assign quiz or test or exam problems of this type. But I am observing that some instructors are doing this. So I really want to give you a heads up on at least get familiar with solving this type of open system, transient flow, steady state, steady flow. So what did we do? We started with a sketch. Always start with a sketch. From the sketch, you figured out it was not open system. It was not steady state, steady flow. It was either, it's an open system, transient flow. Then you planned your work, okay? You start with the fundamentals, not just special formulas for a homework problem. Blindly using formulas is a loser. If you set out to write down bunches and bunches of specialized formulas for specialized problems on a formula sheet that you may be allowed to do, even though I don't recommend it, that's a loser. You get totally confused. And also, finally, you also saw that in my solution, I checked my units. I was consistent with my units as I went along through the solution to keep my units straight. So that's it. And I hope this helps give you a better feel for this third category of thermo problems. It's not closed system. It's an open system, but it's not steady state, steady flow. It's transient flow. And it'll pay you at least to go through this homework problem to get a better feel, better preparation for the potential for a quiz, test, or exam problem.